We are going to put all that we've learned together and answer a problem here. Let's look at example number 16. And we'll look at A first. It says, consider f of x equals 3x to the fourth minus 16x to the third plus 24x to the second minus 9. Find and classify all points where f prime of x, or the first derivative, is equal to 0. Okay, so we need to find the first derivative. And the first derivative, well, is 12x to the third minus 48x to the second plus 48, and that the derivative of just a constant is always going to be 0. And then we want to set this equal to 0. Let me make my pen just a little bit smaller. And so in order to do that, we'll set that equal to 0. So I'm going to first, what can I do here? What am I missing? I see what I did there. There's an x that goes there because that's a x squared. So I'm going to divide everything by a 12x. That's the greatest common factor. And I get x to the second minus 4x plus 4. All right. Now I can factor this. So, all right, 12x. And this factors into x minus 2 squared. If you're not sure how to do that, you need to go back and review factoring. And that's going to be equal to 0. So x is equal to that based on the 0. Like this has to be 0, right? So either this factor can be 0, and in order to make this 0, x would be 0. Or x could be, in here, you set that equal to 0, that would be x is equal to 2. So what we're going to do is we're going to draw a nice little sign diagram. All right, and I'm going to put 0, I'm going to put a 2, and we need to classify what these points are. In order to do that, I'm going to look at what's happening at the first derivative and what is happening at the second derivative, or rather, we'll just stick to the first derivative in this problem, all right? So I'm just going to pick any random point here. I'll pick -1 and try and make it easy. So again, I'm going to plug this number into f prime. So f prime of -1, that would give me, let's see, 12 times -1 to the third power minus 48, -1 to the second, plus 48 times a -1. And this is going to give me a -12. That's a minus 48. And that's another minus 48. 3 negative numbers. I'm going to get a negative number. I don't necessarily need to know the total of this. I just know that this is going to be a negative number. Okay? And that means that the slope is negative. So that means that f of x is going to be decreasing. All right, now I want to check a number between 0 and 2. We'll check 1. So f prime of 1 is equal to 12 times 1 to the third power minus 48 times 1 to the second plus 48 times 1. And that's 12 minus 48 plus 48. You can see this go to 0, and I'm left with 12, which is a positive number. So this is going to be positive. All right, that means that f of x is going to be increasing. Last but not least, we're going to pick a number over here. We'll pick 3. So f prime of 3 is equal to 12. Plug in 3 here. minus 48, 3 squared plus 48, 3. This is going to be a big number. I'm going to just put this in my calculator. And when I do, I get a really big number. Again, what matters here is that you have your sign. Your sign matters most. So this is a positive number as well, which means that f of x is going to be increasing as well. Now, what does that mean about 0 and 2? Well, I'm going to first plug 0 and 2 back into f of x. So f of 0 is equal to, and for our sake, I'm going to try and do this as fast as possible, minus 16, 0 to the 3 plus 24, 0 squared minus 9. You can see that's going to be negative 9. So I have the point 0, negative 9. Okay, we'll come back to that in a moment. And then f of 2, I get 3 times 2 to the 4th minus 16 times 2 to the 3rd plus 24 times 2 to the 2nd minus 9. And again, use your calculator, but just for time's sake, this is going to be 7, so I have the point 2, 7. Okay, I have these 2 points, and they're important. They're important, and we can tell what they are based on the action of the first derivative. So in our previous videos, we've looked at what's going on with this sign diagram. Based on the sign diagram, we can tell that 0, negative 9 is a local minimum. And this is pretty obvious because you can tell it goes from decreasing, f of x goes from decreasing to increasing. So there's a change, right, from increasing and decreasing for f of x. So that's pretty obvious that this is a local minimum. But you might look over here at 2 and the point 2, 7. You might think, it's going from increasing to increasing. Now, if you recall, it's not going to be a local minimum or a local maximum, because a local maximum would mean that this one would have been decreasing. Instead, what we'll have is that this is actually a stationary inflection point. And if you recall, what an inflection point means is that the slope changes, depending on what's happening, from increasing to decreasing or from decreasing to increasing. Stationary means that the f of x doesn't change here from increasing to decreasing or decreasing to increasing. Stationary means that the shape of the graph, so that's increasing, or what's happening in the interval, will stay the same. It'll stay stationary. It'll stay increasing. But the concavity of the graph changes. All right, in A, we found all the stationary points. We found that we have a local minimum and a stationary inflection point at 2, 7. Now in B, it's saying find and classify all the points of inflection. So in order to find points of inflection now, we have to look at the second derivative. In letter A, we found the first derivative, so I'm just going to use that to find the second derivative. So I have 36x squared minus 96x plus 48. And I'm going to set this equal to 0 because that's how you find the points of inflection. So I'm going to divide everything out by 12. And I get 3x squared minus 8x plus 4. That's equal to 0. Now, if you're not sure how to factor this into parentheses, you might go back and practice factoring. But what you do is you multiply 3 times 4 to get 12, and then think in your head, what factors of 12 would give me negative 8? And then you split negative 8 at x. That's how I'm going to do this. There's other ways to do this, but so the way I would write this is, okay, 3x squared minus 6x minus 2x plus 4 equals 0, because negative 6x and negative 2x equal negative 8. So it's not like I'm changing the quantity, I'm just breaking this up. Now this is going to help me factor. So what I'm going to do is I'm just going to look at this part right here. I'm going to factor out a 3x. So 3x, that gives me an x left over minus 2. And over here, I'm going to factor out a minus 2. That gives me an x minus 2 equals 0. And notice that now I have these two factors both have an x minus 2 in them. So I can factor this like such. 3x minus 2 times x minus 2 equal to 0. And you can see that if we set this one equal to 0, 3x minus 2 equals 0, you get x equal to 2/3. If I set this one equal to 0, you get x equal to 2. All right, now let's draw a sign diagram. And we have 2/3 and 2. All right. We have to plug numbers in that are before each point. So let's plug in 0, let's plug in 1, and let's plug in 3. All right. So this time we're checking with the second derivative. So f double prime of 0. Well, you can see that's just going to be 36 times 0 squared minus 96 times 0 plus 48. And you're just going to get 48, which is just a positive number. All right, which means that on this interval right here, f of x is concave up. All right, let's plug in 1 to the second derivative. And we do that, I get 36, 1 squared minus 96 times 1 plus 48. And I put this in my calculator, and this is going to be, actually this is just going to be about a negative number. So I'm just going to make this a negative. So that means that this will be negative, which tells me that my f of x will be concave down. And last but not least, we have f double prime, oops, not of x, but of 3. And again, I'm just going to use my calculator here because we're not necessarily trying to see if we can plug numbers in. That's not what we're learning today. We're just learning about inflection, stationary, how all this kind of comes together. And that is going to give me a positive number. So my second derivative is positive, which means that then this graph at f of x will change concavity and be concave up. So this means that, well, what does this mean about 2/3 and 2? Well, we've got to do the legwork here of plugging 2/3 back in. And when I plug 2/3 back in, just for our time's sake, you're plugging it back into this original function. When you do that, you get about negative 2.48. And when you plug in 2, well, we already got 2 from the previous problem, right? It's going to be 7. And we've already identified, actually, with 2, 7. So we know that 2 comma 7, we know that this is going to be a stationary inflection point, right? We know that it's going to be a stationary inflection point up here because we know that there's no local min or max happening at 2 in the first derivative. But you can see with the inflection point, right, when we look at the inflection points with the second derivative, you can see that it changes concavity. So if it changes concavity, but it doesn't change increasing or decreasing, then we call that, again, a stationary inflection point. So we'll just write that again. 2, 7 is a stationary inflection point. And the point 2/3 negative 2.48, well, this changes concavity and it's all, oh yeah, so it just changes concavity. So that's just, it's going to mean that that is a non-stationary inflection point. Non-stationary, again, means that the concavity will change and that it doesn't really have any impact on the increasing, decreasing guy here in the first derivative, okay? There's our answer. Moving on to C, it says find intervals where the function is increasing and decreasing. Now, if you want to find increasing and decreasing, that involves the first derivative. Well, good thing we've already found the first derivative. So if we go back up here and look at letter A, and we just look at this part right here, you can see that we found that it is decreasing everything less than 0, and it's increasing, right, everything to the right of 0. So that makes letter C a lot easier. So I can say that f of x is decreasing when for x less than or equal to 0. And f of x is increasing for x greater than or equal to 0. Now, it's okay that we include 0 in both of these because we're more concerned about the interval. So I'm not necessarily worried that what's happening at the point 0. I'm worried what's happening over the interval. In D, it's asking us to find the intervals where the function is concave up or down. Now, again, when we're looking for concavity, we look for our second derivative. And again, we've already found those. So you can see in this right here, it tells us where we're concave up and concave down. So we can just copy that down. We've already done that work. That's good. So f of x is concave down for, let's see, for x in between 2/3 and 2. So 2/3 and 2. And f of x is concave up for x less than or equal to 2/3 and x greater than or equal to 2. And there. In E, it's asking to sketch the function and showing all the features that we found. So we're going to use everything that we've found up to this point to sketch the function, this function right here, without using a calculator at all, okay? So let's first start with our points that we found. We found that 0, -9 is a local minimum. So I'm going to go to 0, -9. Again, I'm just going to kind of estimate my points here. So that's 0, -9. And now that's going to be a local minimum. So it's going to be something like, well, let's just start with the points here. That's 0, -9. Okay, it says that 2, 7 is a stationary inflection point. 2, 7 is a stationary inflection point. So we'll make this 2, and we'll call this 2, 7-ish. All right. And then we have 2/3, -2.48 is a non-stationary inflection point. So 2/3, -2.4, so 2/3, I don't know, let's be right. -2/3, -2.48, something like right there, maybe, huh? All right. Okay, now, here's where it gets a little bit tricky, okay? So we know that 0, -9 is a local min. So we know that the shape of this graph, we know where it's increasing. We know that it's decreasing for everything less than 0. So we know that it's coming from somewhere over here, and we know that it's increasing for x greater than 0, all right? So how do I put this in? We know that's decreasing here and increasing here. We know it has to go through this point 0, 9. So it decreases for everything less than 0. There's 0. So it's decreasing. We know that 0, -9 is a local minimum. Okay, so that means it has to start going up. And we know that also our concavity, that it's concave up from 0 to 2/3. Now at 2/3 here, right, it switches concavity. So what's going to happen here is it switches concavity, but 2/3 is a non-stationary inflection point. Non-stationary means that the slope does not go to 0. Let me write this down. Non-stationary inflection point. Slope is not equal to 0. But it changes concavity. So it goes through this point here, and instead of it being concave up, it's now going to kind of start to move like it's concave down. Remember, we got to aim for 2, 7 here. Now at 2, 7, we know that it also changes concavity, because right here, it changes concavity to concave up. And 2, 7, we said that 2, 7 is a stationary inflection point. A stationary inflection point, the slope is equal to 0. So that means it gets about horizontal right here. And we know that what happens next, it does not go down. The reason that doesn't go down is because if you look at here, you see that to the right of 2, it's always increasing. So this has to be increasing everything to the left of 2. So it almost goes horizontal, and then it'll kind of have this action right here. And there you have a rough sketch of y equals f of x. It's important to use your key points. And if you use your key points, then you should have a sketch that looks similar, very similar to this. Obviously, it can't be exact, but very similar to this.